Welcome back. So we talked about linear regression and softmax classification or linear classifications as two basic neural network architectures, where all we had was a layer, our input layer, which was directly connected to an output layer. Now, in this lecture, we want to talk about the need to have hidden layers, so more complex deep learning architectures. To do that, again, we're going to talk about the binary classification problem that we introduced in our earlier lecture on basics of machine learning. Okay, so we're going to consider, again, the goal is to explore why we need hidden layers. So we're going to consider binary classification with hinge loss, something we talked about before. Okay, so in particular, what I'm assuming here is that in the I have let's say two classes, plus and minus, and here I'm going to assume that the data is linearly separable. Again, something we talked about before. Okay, so therefore the classification problem is going to be reduced to finding this separating hyperplane. Okay, so I'm going to therefore assume that the relationship between the labels and features is given by this this expression. So all I need to find is this W, right? So if the inner product between X and W is positive, therefore the data belongs to the positive class. Otherwise, the data belongs to the negative class. Okay. So basically, W is something like this. So I just want to find this W. And the loss that we typically use here is hinge loss because it's a convex function. So we can easily optimize it. Okay. Now, what is our algorithm to optimize this loss? Let's look at SGD. Okay. So what's the SGD for this problem? We have an iterative algorithm. Let's say capital T iterations. Every time we're going to choose a sample, this basically means that I'm going to select a mini batch from the training data, and I'm going to perform the SGD update. So what was the SGD update? The SGD update was W. The next W was the current solution minus some learning rate times the gradient. Okay, so, or we use GT. Now it turns out that the gradient of this function is going to be basically given by these two lines. Okay, so these two lines are essentially my SGD update, where I'm going to look to see whether my current solution is making a mistake on this current data or not. So if my current solution is not making a mistake, I'm not going to update my parameter. But if it is making a mistake, I'm going to update my parameter. Okay, and this again, this update is exactly nothing but the gradient of this max, this hinge loss. So given that the hinge loss is basically is not going to be differentiable in this point, therefore we expect to see these two lines representing our gradient update. Okay. So therefore we can use SGD to learn this parameter W, the parameter of this separating hyperplane, and therefore hopefully we can classify the data. In fact, this method is called perceptron. Okay, and it is going to work very well when the data is linearly separable. Notably, we can derive a simple result that shows that if there is a margin rho between class positive and class negative, then we can get a guarantee on the number of mistakes that perceptron makes. And the guarantee is actually inversely proportional with margin square. Okay? So we are bounding the number of mistakes, basically, if the data is linearly separable, and then we have this non-negligible gap between the two classes. But the question arises here. What if the data is non-linearly separable? Okay? Can we still use this idea or not? And the answer is no, right? So as we can see here, the performance highly depends on linear separability and also a non-negligible margin between the two classes. So if the data is not linearly separable, essentially this margin is zero, right? So therefore we're not going to have any bound on the number of mistakes of this perceptron algorithm. And in fact, there are examples, such as the one that we're going to talk about next, that basically show this simple method is going to fail, meaning that it will never stop making mistakes. Okay? So let's talk about this example then. So we're going to consider a very simple example where we have only two features. Okay? So x1 and x2, and the relationship between the label and the feature is given by the exclusive or XOR operator. So this is a logical operator that you may have some familiarity with it. If not, I'm defining it here. So again, it is operating on bits, binary quantities. So the XOR between A and B is going to be calculated with, first of all, is shown with the symbol, and then it can be calculated with this table. So if both A and B are 0, the outcome is actually 0. If one of them is 1, the other one is 0, the outcome is going to be 1. And finally, if they are the same, so again, and both are taking the value of 1, the outcome is going to be 0. Okay. So let's first of all visualize how the data will look like in this 2D surface, x1, x2. Okay. So as I said, if both of them are 0, the outcome is 0. So let's denote that with 0. Okay. If both are 1, the outcome is again 1. But if both are, if one is 1, the other one is 0, the outcome is actually 1. Okay, so let's use a different symbol here, 1. Okay, so therefore I have two classes, and are these two classes linearly separable? I hope it is clear to see that they are not. Okay, so to separate these two classes, I need a highly nonlinear classifier. So my perceptron model is not gonna work. So how can we approach, therefore, solving this problem? The idea is actually a very neat idea, and it requires combining multiple perceptrons in a specific way. So for this problem, what we can do is to go back to the properties of the XOR operator. It turns out that the XOR can be, if you will, decomposed in these two specific ways. So this way and that way. Essentially, you can utilize the AND operator, the OR operator, and the complement operator to represent XOR. So what we're going to do then, we're going to do this decomposition and combine perceptrons together, such that we have multiple labeling rules. Each one individually leads to a linearly separable classification problem. So we can use perceptrons, and then once we combine them, we can actually therefore classify the data. Okay. So in particular, I'm going to follow this second decomposition, and I'm going to call this one O1, the second term O2, such that the final rule is the AND of O1 and O2. So as we're going to talk about in the next slide, the labeling rule O1 is actually leads to a linear separable problem, same for O2 and same for O3. So each one individually can be tackled with perceptron, and then if we combine them using this idea, therefore we can solve the original non-linearly separable problem. Okay. So this is basically, again, our individual labeling rules. So here we want to demonstrate that, again, they individually are linearly separable problems. Okay. So let's try to, therefore, plot them here. Again, I'm going to consider for all cases, the plane given by x1 and x2. Okay. So let's see how each case will look like. In this case, I have O1, O2. First case I have x1, x2, and the second case I have x1 bar x2 bar. Okay. So the first case, when x1 is 1 and x2 is 1, or 1 is going to be 1. So I have a 1 here, let's say. But if both are 0, I have 0. If first one is 1, second one is 0, I have 1. So here I have a 1. And then secondly, I have a 0 here. So as you can see, they are linearly separable. Okay. So let's also go over the second case. So if both are 1, then I have a 0. So I have a 0 here. If both are 0, I have a 1. So there's a 1 here. If x1 bar is 1 and x2 bar is 0, I have 1 here and then 0 here. So again, linearly separable. And finally, in this case, the last case, if both are 1, I have 1. Both are 0, I have 0. Then I have a 1 here. Then I have a 0 here. And again, they are linearly separable. So I can use a perceptron to handle each case separately, but that's not enough. What I'm looking for is to basically handle the label rule given by that XOR operator. So I have to combine the outcome of these individual perceptrons to find a nonlinear classifier for the original problem, which entails nonlinearly separable data. Okay. So therefore, as I mentioned, each rule can be learned by a single perceptron. And again, we think of this perceptron as essentially a neuron with a sign activation function, because each one is looking at basically the sign of the inner product between the feature and its parameter W, and if the sign is positive, it's gonna return plus 1. If the sign is negative, it's gonna return minus sign. Okay. So, and as I mentioned, to find the label rule, we are basically combining these perceptrons, these neurons, if you will, with this sign as activation function to build what we call a multi-layer perceptron. Okay. So in particular, we have an input layer here, and then we have a hidden layer, and then finally we have an output layer. So this layer is actually new compared to our representation of linear regression and softmax classifier. And we need it here to basically make sure that our model is capable of handling nonlinear data or nonlinear separable classes. Okay. Now, it is actually possible to talk about this in terms of increasing the learning capacity of our model, and we can actually formalize this idea. So MLPs, multi-layer perceptrons, lead to a higher learning capacity, and we can characterize this by a notion we call in a statistical learning theory VC dimension. Okay. So what's VC dimension? It is not very important for us, but the main idea is that VC dimension is the size of the largest data set of points in general positions such that our model can classify. So for instance, in R2, VC dimension of a linear model, such as perceptron, is actually 3. Because if I give you any sort of labelings of 3 data points, you can classify each perfectly, right? And general position means that we should ignore the degenerate cases, where, for instance, all the parameters, all the data points lie in one line. Okay, so that's what it means. Now, it turns out that the VC dimension of the perceptron is actually roughly D. In particular, it's D plus 1. But for multi-layer perceptrons, where we have hidden layers, let's assume that we have L hidden layers. The VC dimension is actually roughly L times D. So by adding these hidden layers, we are increasing the VC dimension of our function class, and that basically means that we are increasing the learning capability of our function class. So therefore, we should be able to handle more complex data. All right. So we mentioned that perceptron is actually like a neuron with the sign activation. Okay. And multi-layer perceptron is basically a combination of a bunch of these neurons in a specific way. Okay. Now, because we want to use computational tools such as gradient-based methods to optimize the parameters of a model, it turns out that the sign activation is not going to be quite easy to deal with. So therefore, there's been a lot of research in the past few decades to find a good approximation to the sign activation. And here I'm talking about basically three of these, the most famous activation functions. Okay. Again, the idea is that we want to approximate, if you will, the sign. Okay. So the first activation function is called the sigmoid activation. Okay. It's given by this expression, and the second one is the tanh. Again, tanh activation given by this expression, and finally we have the rectified linear unit, which is given by this expression. Okay, and here I'm showing how each one looks. So and again, you can compare this with the step or the sign activation here. Okay. Notice that all of these are nonlinear. Okay, so all four of these activations are nonlinear, and this is something very useful. In particular, we're not approximating the sign with a linear activation. Okay, so we don't have, let's say, sigma of x equal to x. We don't have anything like that. Okay, and this is something I'm going to talk about in a minute. Now, among these, we have observed empirically that ReLU actually is a lot more capable. It leads to more efficiency in computation and also more stability in training. Okay, so that's why among these, I would say the ReLU activation and its extensions are more popular. And finally, one remark here is that activations are applied coordinate-wise. I mean that if x is a vector, for instance, if x is equal to 1, 2, 3, then I apply the activation functions in a coordinate-wise way, such that if this is in R3, the activation is also in R3. Okay, so let's make this to -1. So therefore, for instance, for the case of ReLU, the activation of the ReLU applied to x is basically nothing but 2, 3, because these two are non-negative, and then -1 is negative, so therefore I'll just replace it with 0. Okay. All right. So I mentioned that we don't use linear activation to approximate the sign activation, and the reason for that is that if we do so, we're gonna lose the increase in learning capability of our model. Okay, so let's see why that's the case. Let's consider a scenario where we have two hidden layers in our multi-layer perceptron with linear activations. Okay, so in particular, let's say I have the input, I multiply with W1, add some bias, and then I don't apply any nonlinear activation. Therefore, the output of the first hidden layer is H1, and then I feed it to the next hidden layer. And that means that I multiply with another weight matrix W2, add a bias, and then I get my output H2. Now, it is actually very easy to see that these hidden layers will collapse into one. Okay, so this model is actually equivalent to another model where I have only one hidden layer. I directly go from X to, let's say, H tilde with two new parameters, W tilde and B tilde. And W0 and B0 actually depend upon W1 and W2, and B1 and B2, as I'm showing here. Okay, so this is not desirable. Why? Because we talked about the fact that increasing the hidden layers could increase the learning capability. Okay, but if we use a linear activation function, regardless of how many layers we have, that's essentially a one-layer, multi-layer perceptron. So we're not going to be able to increase the learning capability by increasing the layers of the model. Okay, so therefore we aim to avoid such scenarios, and to do that we're going to always utilize nonlinear activation functions such as ReLU. So that's basically a short introduction to perceptron and multi-layer perceptron. In the next lectures, we're going to talk about some other architectures that we typically use in deep learning today. And the main idea is that we want to have architectures that can handle different types of data, and also they can leverage structures that are very frequently present in the data. I'll see you next time.